Hi there, welcome to this AS Physics tutorial. It's tutorial number 4 and it deals with multiple choice questions on error and uncertainty. Please note that the questions in this tutorial are based on 20 past exams. In question 1 it says, a student uses the volume of a metal coin in order to determine the density of the metal. What is not needed in order to determine an estimate of the volume of the coin? So let's start by drawing the coin. To find the volume of this coin, we need the area of the base, which is a circle, and the thickness of the coin. So essentially, we will be using the volume of a cylinder, which is pi r squared h. And h, of course, here is the thickness. So let's see what we don't need. Do we need an estimate of the diameter? Yes, we do, in order to get the radius. Do we need an estimate of the mass? There's no mass in this equation. So the answer is actually B. We know we need an estimate of the thickness because that will give us the height. And we are also using the formula for the volume of a cylinder. Then in question 2 it says, what is a reasonable estimate of the volume of an adult person? Let's start by drawing the person. Now, in order to estimate the volume, we need 3 dimensions. We need the width, we need depth, and we need height. And then to get the volume, we would multiply these 3 quantities. So let's try and estimate what they will be. I would say the width is about 0.5 meters or half a meter. The depth about 20 centimeters or 0.2 meters. And to get the height, we can see that the mass of the person is concentrated over a height of about 1 meter. So times 1. And this will give us an estimate of the volume. If we multiply this on a calculator, we get 0.1. And that will be cubic meters. So the answer in this case will be A. Let's look at 3. It says, what is a reasonable estimate of the kinetic energy of a car traveling at the speed of 30 meters per second? So here we need to know the formula for the kinetic energy of an object. It's a half mv squared. We also need to know the estimate of the mass of a car, and that is 2,000 kilograms. And of course the speed is 30. We can do this on a calculator and it comes to 900,000 joules. Of course we can rewrite this as 9 times 10 to the 5 joules. This is not an answer here with the options, or it's not an option in these answers. But if we rewrite this value as 0.9 times 10 to the 4 joules, then this is approximately equal to 1 times 10 to the 4 joules, or 10 to the 4 joules. So the answer here will be B. Then in question 4 it says, what is the best estimate for the number of atoms in a piece of metal of volume 50 cubic meters? So we can first try and estimate the volume of one atom. And here you need to know that the diameter of an atom is approximately 10 to the negative 10 meters. Now, if you regard one atom as a cube and then find the volume, it will be a cube of sides 10 to the negative 10 meters by 10 to the negative 10 meters by 10 to the negative 10 meters. And to find the volume, the volume of one atom, we will take 10 to the negative 10 meters and we'll cube this. And of course, this will be 10 to the negative 30 meters cubed. So this is the estimate of the volume of one atom. We have a volume available which these atoms can occupy of 50 cubic meters. So to get the number of atoms, we'll take the space available or the volume available, which is 50, and we'll divide it by the volume of one atom. Now, on a calculator, this comes to 5 times 10 to the 31. So atoms. And then, of course, the answer is D. Then in question 5, it says, a student wishes to build a scale model of the solar system in a classroom using a football of radius 0.12 meters to represent the Earth. The radius of the Earth is approximately 6.4 times 10 to the 6 meters, and the radius of the Moon is approximately 1.7 times 10 to the 6 meters. Which object would best represent the Moon? So, if we use a football of radius 0.12 meters to represent the Earth, which of these objects can we use to represent the Moon? We can start by finding this ratio, the ratio of the radius of the Moon to the radius of the Earth. And that's going to be 1.7 divided by 6.4. We can ignore the 10 to the 6 because that would cancel anyway. This we can do on a calculator, and it's 0.265625. What does this answer really mean? It means that the radius of the Moon is approximately 27% of the radius of the Earth. So to find the appropriate object, we need to find this percentage of the radius of the football. And that will give us the radius that we need. So the radius that we need will be 0.265625 times, so approximately 27% of 0.12 meters. And this comes to 0.032 approximately. Or, and of course this is in meters, so it will be approximately 3.2 centimeters. So approximately 3.2 centimeters. Now, which of these objects will have a radius of approximately 3.2 centimeters? And I would say a tennis ball. The diameter of a tennis ball is between 6 and 7 centimeters. So the radius then would be approximately 3.2. Then number 6, what is a reasonable estimate of the cross-sectional area of a wire in a paper clip? Here we need to know that the diameter of the wire in a paper clip is approximately 1 millimeter. So the radius then will be approximately 0.5 millimeters. And this of course is 0.5 times 10 to the negative 3 meters. Now, to get the cross-sectional area, we need to find the area of the circle. And we know the area of a circle is pi r squared. So it's going to be pi times the radius squared. And this comes to, on a calculator, it comes to about 8 times 10 to the negative 7. So approximately 8 times 10 to the negative 7 meters squared. And then of course the answer is C. Then in question 7 it says, a student wishes to measure a distance of about 10 centimeters to a precision of 0.01 centimeter. In other words, a precision of 1/100th of a centimeter. Which measuring instrument should be used? We can draw up a little table for the maximum length that each of these instruments can measure, as well as the accuracy. So a meter rule can measure a maximum length of 100 centimeters or 1 meter, and the accuracy is only 1 millimeter. This is the smallest division on a meter rule. Then a micrometer can measure up to 2.5 centimeters, more or less, and with an accuracy of 1/1000th of a centimeter. So 0.001 centimeters. Then a tape measure can measure various lengths of up to 30 meters. So you have tape measures of 10 meters, 15 meters, 20 meters, up to 30 meters. And the accuracy here, or the smallest division, is only 1 millimeter. Then the vernier calipers can measure up to 15 centimeters. And the accuracy is 1/100th of a centimeter. So 0.01 centimeters. Now, just looking at the precision, we can see that we can discount the meter rule, the tape measure, and the micrometer. We want a precision of 0.01 centimeters, which is given by the vernier calipers. Then the length as well tells us that it must be a vernier calipers, because this is 10 centimeters, which is more than the maximum length that a micrometer can measure. So the answer here will be D. Then in question 8 it says, a student intends to measure accurately the diameter of a wire, which is known to be approximately 1 millimeter, and the internal diameter of a pipe, which is approximately 2 centimeters. What are the most appropriate instruments for the student to use to make these measurements? Now, in this question, unfortunately, we are not given the accuracy required. So we have to choose between the micrometer and the calipers. So without considering the accuracy of the measurement, it's important or worthwhile noting that when we measure lengths of approximately 1 millimeter, we will always use a micrometer. A micrometer is more accurate than a calipers. And then for the diameter of the pipe, which is 2 centimeters, we can use a calipers. So a calipers would be more suitable to measure a few centimeters with if we are not taking into account the accuracy. So then the diameter of the wire will be a micrometer, and the pipe will be a calipers. So the answer here would be C. So in question 9 it says, a micrometer screw gauge is used to measure the diameter of a copper wire. The reading with the wire in position is shown in diagram 1. The wire is removed and the jaws of the micrometer are closed. The new reading is shown in diagram 2. So let's first find the reading in diagram 1. So we have 2.5 millimeters. So 2.5 millimeters. So just to note that one division here is 1 millimeter. And this would be 0.5 millimeters from here to here. Now we look at this vertical scale here, and we can see that this line here meets the vertical scale at about 9. So then plus 9. But each of these divisions on the vertical scale represents 1,000th of a centimeter. We want the reading in millimeters, so it will be 100th, which is 1,000th times 10, so 100th of a millimeter. So we have to divide this by 100. So then the actual reading on the micrometer will be 2.59 millimeters. Let's go to diagram 2. Now, this question is actually about a zero error, or the zero error. If there wasn't a zero error here, but maybe let's just talk about a zero error. It's when an instrument shows a reading when it's not being used. So here we have a zero error. And why do we have a zero error? Because this vertical line, rather horizontal line here, doesn't meet up with 0 on the vertical scale. We need to see where this horizontal line here meets up with the vertical scale. And if we compare these two drawings, it's a bit difficult to see, but it's at about 14 here. This line here, the horizontal line, meets up with 14 on the vertical scale. So that tells us that it's a zero. We have a zero error. Now, what is the zero error here? It's going to be 14 divided by 100. Because remember we said that each of these small divisions on the vertical scale represents 1,000th of a centimeter. And if you multiply that by 10, then it's 100th of a millimeter. So this is 0.14 millimeters. Then to get the final answer, we have to subtract the zero error from the actual reading. So it's going to be, so the actual measurement will be 2.59 minus 0.14 millimeter or millimeters. And that, of course, will give us an answer of 2.45. So it's going to be B. In question 10, it says, the diameter of a solid metal sphere is measured using a micrometer screw gauge. The diagram shows an enlargement of the shaft of the micrometer screw gauge when taking the measurement. So the micrometer shows the diameter of the sphere. We're also given the mass of the sphere, and we need to find the density. So we know the formula for density is mass per unit volume. And we're given the mass here. We have to write this in kilograms though. And we need to find the volume of the sphere. You need to know that the formula for the volume of a sphere is 4/3 pi r cubed. We can read the diameter off here. This is 4.5. So the diameter is 4.5 plus, now there are 31 small divisions here. So we have to divide it by 100. And this is 4.81 meters, or rather millimeters. This we have to convert to the radius. So we're going to divide the diameter by 2. So 4.81 divided by 2 And now we just plug into this equation for the volume here. So 4/3 pi r cubed. Of course, here we have to convert to meters, so it's times 10 to the -3. And this is all cubed. On a calculator, this comes to 7,720 kilograms per cubic meter. So it's C. Here it says a 0.10 kilogram mass is taken to Mars and then weighed on a spring balance and on a lever balance. The acceleration due to gravity on Mars is 38% of its value on Earth. What are the readings on the two balances on Mars? Assume that on Earth G is equal to 10 meters per second squared. Now, we know that your mass will remain the same no matter where you are in the universe. So we can see that the mass will still be 0.10 kilograms. Then the weight is given by the formula mg, and this will vary from place to place in the universe. So m is 0.10. G will be 38% of 10. So 10 times 0.38. And this is equal to 0.38 newtons. So which answer corresponds to these two? And of course the answer is B. So it says a copper pipe has a true diameter of 42.03 millimeters. A builder measures the diameter of the pipe 5 times using a digital calipers, and we are given the measurements here. What describes the builder's measurements? Accurate and precise, accurate but not precise and not accurate, precise but not accurate. If you look at these repeated measurements, we see that they are all close to each other. So that means they are precise. So remember that precision refers to how close repeated measurements are to each other. Then the true diameter is 42.03 millimeters. If we take the average of these values, we can see that they are quite far, or that it's quite far from the true value. So that means it's not accurate. So accuracy refers to how close the average of the repeated measurements are to the true value. So it's precise but not accurate. And that, of course, will make it D. A value for the acceleration of free fall on Earth is given as 10 plus minus 2 meters per second squared. Which statement is correct? Is the value accurate but not precise? Both precise and accurate? Neither precise nor accurate? Or is it precise but not accurate? Now, looking at what's given here, we know that the true value of G is approximately 9.81. And the measurement for G here is 10, which is very close to 9.81. So the measurement value is close to the true value. So that means it will be accurate. If you look at the range of values, the range will be between 10 minus 2, which is 8, and 10 plus 2, which is 12. So this is quite a wide range. So it's not precise. So it's accurate but not precise. So let's see which one it is. Of course, here it's A. Let's look at question 14. It says a measurement is taken correctly, but with a ruler at a significantly higher temperature than that at which the ruler was calibrated. The higher temperature causes the ruler to expand. What describes the effect on the measurement caused by the higher temperature and how the measurement may be improved? And we are given these options. For example, the measurement will be subject to a random error here in B, a systematic error in C, and in D also systematic error. Now, we first need to decide whether the error is random or systematic. Now, remember that a systematic error occurs every time we take a measurement. So, since the ruler has expanded, and we're assuming that this higher temperature remains constant, the ruler will stay at the expanded length. In other words, whenever we take a measurement or make a measurement, an error will occur. So we know that this is a systematic error, because a systematic error occurs every time we do a measurement. So it's between C and D. Indeed, it says the measurement can be made more accurate by taking the average of several repeated measurements. This is incorrect, because we cannot make a measurement more accurate by taking repeated measurements, since every time we take the measurement, there will be an error. So it has to be D. Indeed, says the measurement can be made more precise by taking the average of several repeated measurements, and we know this is true. We can improve on the precision of a measurement by taking the average of several repeated measurements. So here it says, a student determines the acceleration of free fall by using a small metal ball as shown. When the switch S is opened, so when the switch is opened, the ball is released from an electromagnet and an electronic timer is started. So the ball then falls vertically downwards. The timer stops when the ball hits the trapdoor. The student measures the distance PQ, so this distance between the electromagnet and the trapdoor. This distance and the reading on the timer are then used to calculate the acceleration of free fall. So immediately we can see that if the student uses this distance as the height through which the ball drops, it will be wrong. Because let's throw the ball over here. We would have to take into account the diameter of the ball and subtract it from PQ in order to get the correct height through which the ball drops. This is an error that will occur every time. So every time we use PQ in our calculation, we will get a wrong answer. So we know it's a systematic error. And how can we improve on it? Or how can we reduce the systematic error? By taking the distance PQ and subtracting the diameter of the ball. So the answer then here will be D. It's a systematic error, and we can reduce it by subtracting the diameter of the ball from the distance PQ. In question 16 it says, when performing an experiment, a student should minimize the uncertainty of any measurement. In which case is a student reducing the systematic error in a measurement? And in A we have adjusting a voltmeter needle pointer to the 0 position before using it to measure a potential difference. Is this a systematic error or dealing with a systematic error? This is referring to the 0 error. Recall that a 0 error is an error when an instrument gives a reading when the reading should be 0. In other words, when it gives a reading when it's not being used. And we know that the 0 error is a systematic error because it will occur every time the instrument is being used. So the answer here will be A. The rest of these options deal with random errors. Remember, when we repeat measurements, we are reducing the random error. So for example, measuring the diameter of a wire at several points and orientations, this will be in order to reduce the random error. In C, we're measuring the mass of 100 paper clips to determine the mass of one paper clip. So here we are repeating the measurements, and hence it's referring to a random error. And the same in D, timing 20 oscillations of a mass on a spring to determine the period of one oscillation. This is repeating the experiment in order to reduce the random error. In question 17 it says, a digital meter has an accuracy of plus minus 1%. The meter is used to measure the current in an electrical circuit. The reading on the meter varies between 3.04 and 3.08 amps. So it doesn't stay fixed. What is the value of the current with its uncertainty? In all four options here, the value of the current is given to be 3.06. And that's just the average between these two values. So adding them and dividing by 2. We need to find the absolute uncertainty, delta I. Now, if the meter didn't vary between these two values, the absolute uncertainty would simply be 1%, so 0.01 of our reading here, 3.06. But now since the meter varies, we have an additional uncertainty of half the range. So half the maximum value minus the minimum value. And on a calculator, this comes to approximately 0.05. So our answer here will be C. Let's look at question 18. It says the sides of a cube are measured with calipers. The measured length of each side is given by 30.0 plus minus 0.1 millimeters. So basically the measurement with its absolute uncertainty. The measurements are used to calculate the volume of the cube. What is the percentage uncertainty in the calculated value of the volume? So we know that, let's draw the cube. We know that to find the volume of a cube, we take this length, which we can call S, the width of the base S and the height S, and multiply them together. So the volume of the cube will be given by S cubed. We need the percentage uncertainty in V. And remember that when we raise a quantity to a power, we multiply its percentage uncertainty by the power. So the percentage uncertainty in V will be the percentage uncertainty in S multiplied by 3. And we can plug in values. Delta S here is 0.1. S is 30.0 multiplied by 100 and then by 3. And this on a calculator comes to 1%. So the answer here will be C. So here it says a micrometer screw gauge is used to measure the diameter of a wire. The reading on the micrometer with the jaws closed is negative 0.05 plus minus 0.02 millimeters. The reading with the wire in position between the two jaws is positive 1.03 plus minus 0.02. What is the diameter of the wire? This is referring to a zero error. So when the jaws are closed, the reading is not 0. It's negative 0.05. And with a wire in position, it's positive 1.03. So to get the actual diameter of the wire, we need to take our reading with a wire in position and add 0.05. So that's 1.08 millimeters. So our answer here would be B or D. What do we do with these absolute uncertainties? Remember that when we add values or measured values, we add the absolute uncertainty. So it's going to be 0.02 plus 0.02, which is 0.04. So it's going to be D. Then in question 20 it says, 4 identical rods have a square cross-section. The rods are placed side by side and their total width is measured with a vernier calipers. So we have the 4 square rods here. The measurement is 8.4 plus minus 0.1 millimeters. So this is the absolute uncertainty of the measurement. And the zero reading on the calipers is 0.0 plus minus 0.1. So the zero reading also has an absolute uncertainty. What is the width of one rod? And we are given 4 options here. So let's find the width of one rod. Now, important to note that when we take the measurement, we have to add the zero error. And here it's 0.0, so it won't make a difference. But the actual measurement will be 8.4 plus 0.0. And then this is the measurement for 4 rods, so we have to divide by 4 to get the width of one rod. And of course, this comes to 2.1 millimeters. We also have to take into account the absolute uncertainty of the zero reading. So the absolute uncertainty of 4 widths will be 0.1 plus 0.1, so 0.2. And why do we need to add the absolute uncertainties here? Remember, for the measurement we added 8.4 to 0.0. So we also have to add the absolute uncertainties, and that comes to 0.2. This is the absolute uncertainty of 4 widths, of 4 rods. So the absolute uncertainty then of one width will be 0.2 divided by 4. And this is 0.05 millimeters. So which of these answers then do we take? It's clearly B. B is the only answer here with an absolute uncertainty of 0.05. Let's look at question 21. A thermometer can be read to an accuracy of plus minus 0.5 degrees centigrade. This thermometer is used to measure a temperature rise from 40 degrees to 100 degrees centigrade. What is the percentage uncertainty in the measurement of the temperature rise? Let's first work out the temperature rise T. And if we call 40 degrees T1 and 100 degrees T2, it will be T2 minus T1. So we're actually doing 2 readings to get 40 degrees for T1 and 100 degrees for T2. And of course, it's just going to be 100 less 40, which will be 60 degrees centigrade. So this is the temperature rise. It's important to note that we get this temperature rise by taking 2 readings and then subtracting the one from the other. We need to find the percentage uncertainty, but before we find the percentage uncertainty, we need the absolute uncertainty in the temperature rise. Now, the accuracy here is given as plus minus 0.5 degrees centigrade, and this applies to each of T2 and T1. So the reading T2 as well as the reading T1 will each have this absolute uncertainty. Now, the rule says that when we add or subtract values, we always add the absolute uncertainties. So we need to add 0.5 for T2 plus 0.5 for T1. And this is 1 degree centigrade. So we have the absolute uncertainty. Now to get the percentage uncertainty in the temperature rise, we need to take the absolute uncertainty divided by the measurement and multiplied by 100. So delta T is 1, T is 60, and we multiply this by 100. And this comes to 1.6 recurring on a calculator, which is approximately 1.7. So the answer is D. Let's look at question 22. It says the speed shown on a car speedometer is proportional to the rate of rotation of the tires. So what does this mean? If the rate of rotation doubles, the speed will double. If the rate of rotation halves, the speed will halve. That is the speed shown on the speedometer. If the rate of rotation decreases by, let's say, 10%, the speed will decrease by 10%. Then it says the variation of the diameter of a tire as it wears introduces an error in the speed shown on the speedometer. So basically the tire wears out after a while, and that affects, or that introduces or causes an error in the speed shown on the speedometer. A car has new tires of diameter 600 millimeters. The speedometer is accurately calibrated for this diameter. Then it says the tires wear as shown, with 6 millimeter or millimeters of material being removed from the outer surface. And in the question is, what is the error in the speed shown on the speedometer after this wear has taken place? We're given these 4 options. Let's look at this in more detail. We know that the diameter becomes smaller and smaller, and eventually it's 6 millimeters smaller, or we have 6 millimeters of wear. But what's important to note, how does the diameter change? So we have to take into account that we would have 6 millimeters here as well as here. So it's actually 12 millimeters. The diameter decreases by 12 millimeters. Let's find the percentage uncertainty introduced. It's going to be, of course, inner diameter. It's going to be 12 divided by 600 times 100. So we can work that out. And that comes to 2%. So the diameter decreases by 2%. How will that affect the rate of rotation? We know that if the diameter is smaller, then the rate of rotation will increase. So for a large tire, or large circumference, we'll have a certain rate of rotation. If we take a particle here, the time it takes to get to the bottom here will be greater than for a tire with a smaller diameter. This particle will take much quicker to get to this point, to rotate. So that means that the rate of rotation actually increases as the diameter gets smaller. And it increases by 2%. Now, remember that we were told that the speed is proportional to the rate of rotation. So if the rate of rotation increases by 2%, that means that the speed given on the speedometer of the car will also increase by 2%. However, the speedometer is calibrated for a diameter of 600 millimeters. Now the wheel is rotating faster. Since the diameter is smaller, it's rotating faster by 2%. And that means that the speed will be too large by 2%. So let's see which answer that is. In A it says the speed shown is too high by 1%, so this is incorrect. The speed shown is too high by 2%. So the answer here will be B. In question 23 it says, a steel ball is dropped and falls through a vertical height h. The time taken to fall is measured using light gates, and the results are given in the table. So we have the measurements for H and T together with their absolute uncertainties. Then it says the acceleration of free fall G is calculated by using this equation. What is the percentage uncertainty in the value of G? We can start by making G the subject of the formula here. So it's going to be 2H over T squared. We want the percentage uncertainty in G, and it's going to be the percentage uncertainty in H plus the percentage uncertainty in T. Remember that when we multiply or divide quantities, we add the percentage uncertainties. We can ignore the 2 here because it's just a constant. So then the percentage uncertainty in G will be the percentage uncertainty in H plus the percentage uncertainty in T. Now, something important to note is that the T is squared, and the rule says that when we square quantities, we multiply their percentage uncertainties by 2. So we have to do this calculation. So the percentage uncertainty in G is delta H over H, so 0.01 divided by 4.05 plus the percentage uncertainty in T, 0.02 divided by 0.91, and of course we multiply this by 2, and then we can multiply everything here by 100. Now on a calculator this comes to 4.6, so 4.6%. So here the answer then will be B. In question 24 it says the power P dissipated in a resistor of resistance R is calculated using this expression, where V is the potential difference across the resistor, and the percentage uncertainty in V is 5%, and in R it's 2%. What is the percentage uncertainty in P? So here we are dividing two quantities, so we know that we must add their uncertainties or their percentage uncertainties. So V is 5%. However, we are raising V to the power 2, and that means we must multiply its percentage uncertainty by 2, so by the power. And we add to that the percentage uncertainty in R. And of course this comes to 12%, so D. So here it says a student attempts to find the density of aluminium by taking measurements of a rectangular sheet. So we're given the mass M, the length L, the width W, and the thickness T, together with their absolute uncertainties. He uses the equation rho, so the density equals mass, or M, divided by WLT to calculate the density. What is the calculated value of the density with its uncertainty? Now, the first thing to notice here is that the answers are all in grams per cubic centimeters. However, the thickness here is given in millimeters. So our first step will be to convert the thickness or the units of measurement of the thickness to centimeters. And of course we can do so by dividing by 10. So it's 0.020 plus minus 0.001 centimeters. Next, we can find the density by plugging into this equation. So the density rho will be the mass divided by the width multiply by the length multiplied by the thickness. And of course that must be in centimeters. And then on a calculator, this comes to 0.26. So we know the answer must be either A or B. Now we can find the absolute uncertainty of the density. But before we can find the absolute uncertainty of the density, we first need to find the percentage uncertainty. So the percentage uncertainty in a row. Now remember that when we divide or multiply quantities, we add their percentage uncertainties. So it's going to be delta M over M plus delta W over W plus delta L over L plus delta T over T. And this we must multiply by 100. So we can fill in our values. So delta M 0.1 divided by M delta W 0.1 divided by W, then delta L over L plus 0.01 over 0.20. We can actually use the measurements here in millimeters because the effect of changing to centimeters will cancel out here. Then on a calculator, this comes to approximately 6.29%. Now to find the absolute uncertainty in the density, in other words, delta rho, we simply apply this percentage to the value we got for rho. So 0.26 multiplied by 6.29 divided by 100. And on a calculator, this rounds to one significant figure of 0.02. So to a one significant figure value of 0.02. And so our answer will be B.